All right, back to easy physics. So here's what we're looking at today. The diagram below shows a simple mass spectrograph. It consists of a source of ions, which are charged atoms, that are accelerated essentially from rest by the voltage V and enter a region containing a uniform magnetic field B. The polarity of V max may be reversed, so positive and negative charge, so positive charged ions, which are cations, and negatively charged ions, which are anions, can be accelerated. Only the ions enter the magnetic field and follow a semicircular path and strike the front wall of the spectrograph with photographic plates constructed to record the impact. Assume the ions have mass m. So wonderful. So here's what's happening over here. You've got particles, charged particles, ions over here. Don't worry about the positive and negative, but you are going to have a voltage source attached to this, and they're going to shoot it this way, and then it's going to bend in the magnetic field. The magnetic field we only care about in here, and the electric field we only care about in here. Nice. Okay, so what is the acceleration of an ion of charge Q just before it enters the magnetic field? So when we're in this area, we are going to have let's double check here. They're accelerated from an enter region containing a uniform magnetic field. Okay. So what we know is that there is some force acting on there, right? So we'll call it the electrical force divided by m. So that's what your acceleration is equal to. Well, this electrical force is coming from the field, right? So you remember your electric field is equal to F over Q. So that means that we can replace that F with E times Q. So we're going to have E times Q over M. So far, so good. So what we're going to do now is replace the E, because remember your voltage is equal to E times D, right? Your electric field times the distance in there. So we're going to swap out this. So E can be replaced with V over D. And then the Q and the M are going to stay hanging out there. And that's it. That's all we can do. And then we have all of this information because there's D, and V is the voltage source, and Q and M is the ion particle. All right, so now let's look at the next one. Find the speed with which an ion of charge Q enters the magnetic field. Well, since we know their acceleration, the acceleration is going to be the same for this guy here. Actually, we can do it easier. Let's use voltage. Let's use voltage instead of kinetics here. So remember that voltage is equal to work divided by charge, right? Energy divided by charge, whatever you want to call it. So if we solve for this, that means the VQ is equal to energy, and that energy is going to be 1/2 mv squared. Right when you're leaving the electrical field is when you have all of the voltage adding up to this here. So if we solve for velocity, we're going to get the square root of 2VQ over M. Big square root. And that's it. Because that's all, or V equals. Ta-da! All right, which semicircular path would a cation follow? All right, a cation is a positive ion, right? So if you have a positive ion shooting this way, let's look at our magnetic field here. Enters forming a uniform magnetic field. Let's strike the. All right, so let's see what it talks about for this. Well, it appears I cannot find it, which way the magnetic field is going, but I check in the book that they have it as being X's. I don't see it on there, so well, that's a mark against them. But anyways, let's just call it X's anyways. Now, using your right-hand rule, if you were traveling to the right and you had the field going in, your thumb should be pointing up. That means your cation, which is a positive, should be accelerated upwards, which means it'll go towards path 1. Now, if it were an anion, it'd be negative and it'd do the opposite, so it'd be path 2. I know it didn't tell you that, but there's nothing else I can do for you about that now. Determine the mass of a cation entering the apparatus in terms of those variables there. Okay, so what do we know? We know the speed of those ions, and we can figure out what the force is, because the magnetic force is going to act as a centripetal force. So, what do we know? We know that the centripetal force is going to be mv squared over r, and that's going to equal the q times the v times the b, right? That's your magnetic force formula. Okay, so far so good. So let's cancel out this guy and this guy. So we're solving for m, but before we do that, we got to plug in the velocity right here. All right, like we figured out before. So we're going to have m times square root of 2 voltage charge over m over r is equal to q times b. All right, we're solving for m. Before we do that, let's distribute the square root here. This square root, we're going to separate those. So you have m divided by the square root of m, which can cancel out to. All right, so far so good. So this will make it a little bit easier because we can merge those square roots, throw the r over. So we're going to get the square root of m2vq is equal to qb. Now we can square everything. So we're going to have, and let's just divide it too, so we can make this jump. M is equal to q squared b squared divided by 2vq. So let's cancel out one of those q's on the top. And that's it. Ta-da! Okay. So what's the last one over here? Or, well, there's 2 more, I guess. New color. Once a cation of charge Q enters the magnetic field, how long does it take to... Oh, sorry. We're not quite done yet with that one. Oh, no. Sorry, yeah, we are. No, we're not. Oh, I forgot the R. That's the problem. So R should be up here, R should be there. Now, what is R going to equal? R is going to be half of Y. That's what I forgot. So since R is equal to 1/2 of the Y, we plug that in. So now, finally, at long last, b squared y over 4v. And that's what we have. That wasn't so bad. Now, was it? Okay, so now let's look at this one here. How long does it take to strike the photographic plate? So the time it takes, well, we have the velocity here, and then, well, we can figure out the distance. So, I don't know, let's go over here. So we know that velocity is equal to distance over time. The velocity is this guy, so that's going to be square root of 2vq over m. And then what we're going to have is equals the distance. The distance is going to be pi times d over 2. Can I just use the diameter one since that's easier? So pi times d, but we want half of that, and there's t. So now we just got to solve for time. So time, bring that up, bring those down, is equal to pi y over 2 square root of m over 2vq. All right, not so bad. What is the work done by the magnetic force in the spectrograph? Oh, that's easy. 0 joules, because the force is perpendicular to the velocity at every instant. Since they're perpendicular, you can't have any overlap between the force times the distance in every instant. So that's why, remember, centripetal force can never, ever, ever do work. I promise. Never. Okay, let's do the next page. A particle accelerator has a collision that results in a photon and anti-bottom quark and a charm quark. Sounds delightful, doesn't it? The magnetic field is that and can be described as into the page. Hey, they told us the direction this time. They're so generous. A photon has no charge and has an upper theoretical mass of that. Yes, this is a relativistic mass, so don't worry about it too much. Just run with what they tell you. The charm quark has a mass of that, and a charge of that, and a velocity of this, and the anti-bottom quark has a mass of this, and orbits with a radius of that. Wouldn't it be a top quark? Oh, no. Sorry. And a velocity and a radius. Oh, okay. This is all this fun stuff. Okay, so what is the orbital radius of the photon? So let's think about this here. So you've got a magnetic field. B is equal to x, and B is equal to 6 times 10 to the minus 8. All right? So that's happening. A photon has no charge. Now, what's going to happen with the photon? What is the orbital radius of the photon? None. Because the photon will not go into circular motion. Why not? Because it has no charge. It's going to just go in a straight line, linear motion. That's a silly one to start with. But whatever. It is what it is. It will not have any circular motion at all. So now, what's the orbital radius of the charmed quark? Now, I don't remember what the symbol is for a charmed quark in particular, but I'll just have to deal with it. Blah, blah, blah. The charm quark has a mass of this and a charge of that and a velocity of this. All right, so that's the only stuff we got to worry about right now. So it is a positive charge. So if our B is going into the paper, we have a positive charge. So that means it's going to be going in this direction. I'll call it C for charm. I know it's not the right symbol, but oh well. So what's happening? You have centripetal motion here. So you have mv squared over r. That's going to equal qvb. All right. Ta-da. So what we're going to do now is we're going to be looking for the radius. We're going to be solving for the radius. So multiplying, boom, 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 boom. So bring the r over. So r is equal to mv squared over, oh, I forgot to cancel all these. So let me get rid of that squared. Whoops. So mv divided by qp. So that's the radius here. So now we just got to plug in these values. So m for charm is 2.23 times 10 to the minus 27 times the velocity is 40.1 divided by q, which is 1.07 times 10 to the minus 19 times b, which is 6 times 10 to the minus 8. So now I just got to type these in. 23 times 27. Yeah, isn't this fun? Typing. Oh, I made a mistake. times 10 to the minus 8. Oh, no, I'm okay. All right, so at that, for a radius, I got 13.9. And that would be in meters because we're using standard units here. Cool. All right, hey, looking at C. What is the charge of the antibottom quark? Okay, so we don't know its charge. Let's just pretend it's going in the same way so we can visualize this. So we'll put B with a line on top of it. We're going to use the same kind of formula here. So we know we're going to have MV, I'm not going to write the squared because I know it cancels and I can look at it, equals QB. All right, so the antibottom quark, we have a mass, we have a radius, and we have a velocity. All right, well, all we're going to do is solve for Q here. So Q is going to equal mv divided by rb. So m is 7.49 times 10 to the negative 27 times velocity, which is 41.5, divided by our radius, which was 92.7 meters, times b is 6 times 10 to the minus 8. All right, so it's typing time, 7.49 minus 27 times 41.5 divided by 92.7 divided by 6 times 10 to the minus 8. So I'm getting 5.6 times 10 to the minus 20. There's the mouse. 5.6 times 10 to the minus 20 coulombs. Hey, is that what they got? Nice. All right. Oh, and it tells us it's in a clockwise manner. So I drew the picture wrong. I didn't read it closely enough. Clockwise manner, so it's going this way. Isn't that a beautiful drawing? Okay. Well, let's just make it easy for ourselves. It's the opposite of the charm. The charm is a positive charge, right? Yep, so that means this is going to be a negative charge. And that's all we need for that one. Easy money. And there we have it.